Thanks everyone for joining us. Today's webinar is all about heat and heat management. I'm Olivia Broadhurst and I'm the coordinator of the Whitsunday Climate Change Innovation Hub. The Hub is an initiative of Whitsunday Regional Council and looks to build resilience of the Whitsundays and communities everywhere to climate change. Since the late 1800s, human-induced climate change has warmed the Earth's average temperature by about 1 degree Celsius, and this is predicted to continue to increase rapidly over the coming decades, making heat one of the largest risks to be managed with our changing climate. Today's webinar shares information on a study completed for the Climate Hub by Mosaic Insights and NCE Economics. The study focused on heat in Proserpine as an example of a typical regional Queensland town. We have two presenters today. Dr. Stephanie Jacobs is going to present details of the heat mapping and modelling completed in the study first. Stephanie is a climate scientist specialising in urban climate and cooling, climate change and heat stress. She completed her PhD research in modelling urban heat mitigation strategies and human heat stress for Melbourne during heat waves from the current and future climate. At Mosaic Insights, Steph conducts spatial urban heat modelling from the street scale up to the local government scale, using a range of microclimate models to determine the best way to cool the urban environment. Stephanie will provide information on how heat is predicted to increase in Proserpine, the areas most vulnerable to heat, and explain the heat mitigation methods that were tested in the study. We will then dive into the cost-benefit analysis with our second presenter, Dr. Bayani Tommy. Bayani is an environmental economist with a PhD in the non-market valuation of urban amenity benefits, natural resources, and open spaces such as waterways and urban open spaces. Since joining NCE Economics in 2017, Bayani has undertaken a number of studies on the value of urban amenity enhancement across green spaces, waterways, and coastal zones. Bayani has worked extensively with Dr. Stephanie Jacobs, integrating urban cooling and economic model estimates. Bayani's presentation will pull together all the science and explain the most cost-effective ways for rural towns such as Proserpine to manage heat into the future. Each presenter is going to provide around a 10-minute presentation, and at the end of the presentations, we will have some time for questions. We ask that everyone please keeps their microphone muted during the presentations. You can also type questions in the chat. If you are having trouble with your quality of your connection, we would recommend that you turn off your video. We are recording the webinar, and as I said, it is going to be available shortly on the Whitsunday Climate Change Innovation Hub website. So without further ado, I'm going to hand over to Dr. Stephanie Jacobs from Mosaic Insights to present the first steps of the study. Thanks, Steph.
Thanks, Olivia. I'll just share the slides for you. Okay, thank you everyone. Thanks for having us here today. It's really exciting to share the results of this really cool work we did for Whitsunday Regional Council. So looking at Proserpine and what the temperature is like in the current and future climate and how we can try and improve it. So this seminar will start with a little bit of doom and gloom regarding climate change. It's a pretty scary prospect, but we will kind of finish with a good news story. You know, there's something we can do about it to really help. So just as a bit of context to this work, you may not know this, but heat waves are actually the deadliest natural disaster in Australia. So they've actually caused more fatalities in the last 130 years since they've caused more fatalities in the last 130 years than all other natural disasters combined. So if you think about floods, bushfires, tropical cyclones, earthquakes, heat waves have caused more deaths than all of them, which is pretty alarming. So they're often described as the silent killer because those who often suffer from heat waves are usually the most disadvantaged or young children and the elderly. So another kind of scary prospect is that climate change is expected to make heat waves hotter, longer, and more frequent. So research that was done found that by 2090, Proserpine is expected to have 45 heat wave days per summer. So you can see that in the map on the north, that the number of heatwave days per summer in 2090 in a high emissions scenario is particularly going to affect northern coastal Australia. The length of the longest heatwave event is also expected to be approximately 20 days, which is quite an alarming length of time in summer. There's also been research that's found that by 2050, the number of days over 40 degrees Celsius in Proserpine is expected to increase by 540%, which is quite a lot, which is about 0.6 days per year. But the number of days over 35 degrees, this is a very hot day, is expected to increase by 205%, or 9 days per year. So there's some pretty scary statistics involved with climate change. But it's also worth considering that 90% of Australia's population also lives in urban areas, whether these are, the large capital cities or smaller towns. And it's these urban areas that also suffer from something called the urban heat island effect. So basically, when you have things like roads, buildings, footpaths, they're these human-made surfaces that really are often darker than a natural environment, and they absorb heat during the day and they can release it at night. Cities and urban areas also feature less surface water, which would normally evaporate and cool a city, but instead it's underground, less vegetation, fewer trees. Then urban areas also just contain hot things like cars, they emit heat, air conditioners, and even people. They can all contribute to the urban heat island effect. So when you consider that heat waves are particularly deadly and they're likely to get worse with climate change, combining that with the fact that most people live in a town or a city and that can suffer from the urban heat island effect, it's a pretty dangerous combination, which led us to the first part of this project, which was looking at what does urban heat look like in Proserpine in the current and future climate. So to do that, we conducted some heat mapping, and we used the target urban climate model, which was developed by the CRC for water sensitive cities. So when you conduct heat mapping, it's quite simple in that you need spatial data for a site, you need meteorological data, you pop it into a model and you get some heat mapping. So this slide here describes some of the spatial data that we sourced for Proserpine. So we used a company called Geoscape, and they have all of Australian urban areas at a 2-metre resolution. So you can see on the left is a Google satellite image of Proserpine and the surrounding areas, and on the right is the data that we sourced from Geoscape. And that became the information that we put into the model. So to give you a bit more of a detailed look at it, we've zoomed in on this area. You can see Proserpine. You can see Main Street up here, and we've got the sugar mill in the northeast of that, northwest, of that image. And you can see the breakdown of the different land use types that are involved in this data. It can look at bare earth, it can differentiate between buildings, roads, swimming pools, and trees. And so what we did was we took that information and we classified it into the spatial information that the model reads. So that's buildings, roads, concrete, dry grass, irrigated grass, trees and water. So we took this data and we put it into the model. Next, we needed meteorological data. So what we did was we took data from Proserpine Airport Weather Station and we looked at the air temperature, the relative humidity, the wind speed, the surface pressure, and some radiation variables like solar radiation. And what we did was we chose a day that is considered, it's not the hottest day that's ever occurred in Proserpine, but it's still quite a warm one, where the temperature was 37.5 degrees. This is quite a hot day. And so what this graph in the center shows is how the temperature rose throughout the day and also how the relative humidity changed. And it actually decreased during the day as the temperature got hotter. So that's the information that we put into the model, into the heat mapping model. But we also wanted to know how is the temperature going to change in the future climate. So what we did was we got climate model data from 8 different climate models and aggregated them and looked at how that will change in Proserpine. We used the high emissions climate change scenario, which is, I suppose, the most extreme one in terms of scary climate change impacts, but it's also the the track that we're currently on, which is a bit of a scary prospect. So we looked at temperature data and other variables from the climate models for 2050 and 2090, as these times were the ones that aligned most best with the planning scheme. So by 2050, it was expected that a February day would be about 1.5 degrees warmer, and by 2090, it would be about 3 degrees warmer. So that was the information that we put into the heat mapping. And so here are the results. So what this shows is the map of Proserpine for the temperature on the left in 2018. So that's the current climate. We chose this 37.5 degree day. And what's interesting is that at Proserpine Airport, it was 37.5 degrees, but in the town, it reached a maximum of 40 degrees. And it's interesting to notice that some of the hottest areas in the town were the sugar mill, the hospital, where lots of vulnerable people can be, the Catholic college, the nursing home, Main Street, and also the roads. So the roads, I suppose, aren't that surprising when you think of these like asphalt surfaces that can be quite dark, absorbing heat. We also did this analysis for 2050. So in that situation, the temperature at Proserpine Airport would be 39 degrees, but in the centre of town, it would be 41.5. And again, it's quite a lot warmer. And in 2090, the temperature at Proserpine Airport would be about 40.7 degrees, but in the centre of town, it would be 43. So it's quite a big difference. This urban heat island really affects it. It's also worth noting, though, that areas of irrigated grass in some of the sports fields and the golf course, they're quite a bit cooler than the more traditional urban areas like Main Street. And also the areas around the river and some of the more natural areas are also quite a bit cooler. So it's really interesting that they can provide this great contrast in temperature that could hopefully be harnessed to help cool Proserpine. So we've kind of demonstrated that it's going to get hot in Proserpine, and it's going to get even hotter. So, which led us to the next question, which was, how do we reduce this urban heat? And lucky for us, there's quite a few ways to do it. This is where the presentation starts to get a bit more positive. Here's what we can do about it. So we actually looked at 11 different scenarios for how we can potentially reduce urban heat in Proserpine. So the first three were white roads, white pavements, and white roofs. This is when you are painting that surface white. And it's quite a simple concept where basically if it's coloured white, it reflects away the solar radiation, and it means that if it's a white road, the road is not absorbing all that heat. But there is a downside in that they can often produce glare because that radiation is bouncing off the surface and, perhaps going into your eyes. So that's something worth considering. Next, we looked at things that would be defined perhaps as green infrastructure, so misting systems, water fountains, having a pond, having some green walls, and irrigation. And generally, these reduce heat through evaporation. So water requires energy. It takes energy from the air to then be evaporated, so that can create a cooling effect. But some of the downsides of these ones is that they can be expensive to install or sometimes require a regular water source. And finally, we looked at implementing street trees, replacing a hard surface such as like a road or some concrete with grass, or replacing a hard surface with irrigated grasses and trees. And so the idea of this is to reduce the amount of impervious surfaces that are there and try and increase shading through trees. But it is worth noting that sometimes there can be some engineering conflicts, and we know that street trees are not always that easy to implement when considering the driveway crossovers and potential densification limits. So what we decided to do was we ran a really detailed high-resolution modelling study on a case study area that was bounded by Chapman Street, Main Street, Davie Avenue, and Marathon Street. And we looked at some high-resolution 3D modelling of that site. And what we did is we then implemented different scenarios involving these cooling options, like what would happen if we had white roads, and then we looked at what the cooling effect would be. So one of the benefits of conducting this high resolution modelling is that modelling is a great way to try before you buy with cooling options. You can see what works best, you can see what maybe doesn't work that well in Proserpine, but you can also see what might have some unintended consequences. So this case study area we chose, we looked at it because it contained Main Street, which, as the initial study showed, where we mapped the temperature, it's one of the hottest places in the town. It's also quite an urban area. It features car parks, but we also have this green space as the sports fields located in the school. So I'm not going to talk you through the results of every single experiment we did, but I'll talk you through some of the more interesting results. So the first one we did was street trees. So we placed street trees on both sides of the road on the east-west oriented streets, and just on the eastern side of the road on the north-south streets. This is so because on the east-west streets, the sun is overhead throughout the day, but on a north-south oriented street, we want to protect the buildings and shade them from the afternoon sun. So the trees that we simulated were 6 metres high and had a width of about 5 metres, and they were generally placed about 5 metres apart. So what this map on the right is showing you is the cooling effect. So we modelled the temperature of that zone when we had when we didn't have the trees, just as it is currently, and then we added in the trees and we looked at the temperature difference. And you can see that it was pretty stark. There's quite a big cooling effect where these trees were, and the maximum cooling actually exceeded 4.5 degrees. So it really felt a lot cooler under those trees. This is because you've got shading from the trees and evapotranspiration where the trees, transpire water. It's also worth noting, though, that a taller and wider trees would actually increase the cooling effect as they greatly increase the area that's shaded. Irrigated trees will also produce more cooling because they are healthier and have, thicker crowns and canopies. But the reason we chose trees of these sizes is because that's generally what is preferred considering cyclone risk. Another interesting scenario we looked at was irrigated grass. So in the scenario, we irrigated all the grass at the kind of church and school block, and we irrigated at 10 millimetres per hour from 2 a.m. to 5 a.m. And what's interesting is that it had a maximum cooling effect of nearly 1.3 degrees, which is pretty great. And what's also interesting is that the cooling effect actually extended beyond the area of irrigation. So it travelled on the wind, which I think is really exciting and could demonstrate that these cooling effects can often spread beyond just where they've been applied, particularly if it's like a windy day. Research was also done and that found that on days when the temperature is greater than 35 degrees in Proserpine, the wind is pretty much always from the north. So it's worth considering placing the cooling mechanism or cooling option, whichever you could choose, to the north of the hotspots. So this is one of those ones, this is white roads we looked at. So we painted all the asphalt roads white in the model, where they reflected 70% of the solar radiation, where a standard road would reflect only 20%. So we've really upped the whiteness and reflectivity of this road. And what we've done is we then looked at the difference in temperature, and we found that the maximum cooling effect is pretty strong. It's about 1.6 degrees, and it was really applied quite widespread where we painted the roads white, but also it travelled a little bit, cooling a little bit further south of the roads as well, moving into these areas. But this is one of those ones that also had some of the unintended consequences. So when we considered a measure of human thermal comfort, so like the feels like temperature, we measured something called the UTCI, or the Universal Thermal Climate Index. That takes into account things like temperature, humidity, wind speed, and radiation. And so what we found was that when you painted the roads white, they actually reflected the radiation in lots of different directions and actually caused glare and resulted in a lot of the areas of the case study actually feeling hotter once you've painted the roads white, which was quite an interesting finding and really demonstrated some of these unforeseen consequences that could happen. So the final scenario I'm going to talk you through was changing a hard surface to irrigated grass and trees. So what we did was we converted an asphalt road to be replaced with irrigated grass and lined the street with trees. So again, the trees were 6 meters high and 5 meters wide, with the trees placed, again, approximately 5 meters apart. Now, in this scenario, we've used Main Street as an example, but that does not mean we're suggesting to do this to Main Street. It was just an example to use in our case study area. And the results were pretty significant. So again, we found maximum cooling of about 4.8 degrees under those trees, and it's really helped by having that irrigated grass underneath, creating a nice widespread cooling effect. And it really demonstrates that there's some big cooling gains that can be achieved through increasing vegetation. So now I'm going to pass on to Vianney, who will give us a bit of a talk through some of the economics involved with this work.
Thank you, Steph, for that excellent overview of the project, all the sophisticated heat mapping. It was really great to see you work through that. I'll now walk you through the economic side of the project. It's generally helpful to communicate benefits and values in dollar terms. And I've been to conferences where I've heard people mentioning that if you can't measure it, then you can't manage it. So let's take this, as a way to be able to measure the outcomes or the impacts that might come from some of these scenarios that Steph has gone through. And the other thing is that the dollar values, this is essentially the language that is used by decision makers who are often, faced with limited budgets, but have many competing needs for those limited funds. It is important, though, that whatever approach we take to value those benefits is systematic, robust, and transparent. And in this case, we have adopted 2 evaluation frameworks. The first one is called cost effectiveness analysis. This is whereby projects are compared based on their relative performance in achieving a specified outcome relative to the costs. For example, in this case, we are looking at cooling outcomes measured in degrees Celsius. The other approach is the benefit cost analysis, or BCA. This is the primary economic assessment tool used to inform business cases for public expenditure and to help make policy decisions. We use it to analyze the benefits and costs of a project or a policy initiative. The measures or investment criteria in a BCA, or benefit cost analysis, are the benefit cost ratio and the net present value. A benefit cost ratio of greater than 1 implies that for $1 you invest on the project, you'll get more than $1 in terms of benefits. And a net present value of greater than 0 implies that your overall costs are less than the benefits that you have included in your analysis. These 2 measures can then be used for checking the project for its economic viability, and you can also use them to rank and prioritize investments for the different projects. For our BCA, we have followed the Queensland Treasury guidelines, which are summarized in the flow chart on the right there. We started by getting a good understanding of what the problem was and establishing a base case, which is whereby we say what will happen if you don't do anything differently or you do nothing more in this case, to mitigate the heat effects. We then scoped for benefits for the different scenarios that Steph has gone through. And we consulted with the council and other engineers within our group of companies to get some information around the costs of those different options. We then set up a benefit cost analysis model and calculated our NPV, or net present value, and the benefit cost ratios, which I'll cover in subsequent slides. Can you move to the next one, Steph, please? Okay. In this slide, we are presenting our cost effectiveness analysis results. This is a comparison, like I said, a comparison of the project costs to the cooling outcome. As in this case, the cooling outcome is measured using UTCI, or Universal Thermal Climate Index. For ease of communication, the CEA was undertaken by comparing the cooling outcome that can be achieved by investing $100,000. So for every $100,000 you spend, the bar charts here indicate how much cooling you'll get under the different scenarios. Some scenarios appear blank. This is because they were found to have no cooling impacts. These are the adverse impacts I've mentioned. And in other cases, the cooling outcome was relatively very small compared to the costs, e.g. Your white roofs. These results indicate that irrigation is the most cost-effective approach for achieving reductions in temperature, and changing your hard surfaces to trees, or changing those hard surfaces to irrigated grass is ranked second, followed by street trees and grass areas. Next one, please. Okay. We've just gone through the cost effectiveness analysis results. Now we'll focus our discussion on the benefit cost analysis process. This process, or this approach, allows us to look beyond just the cooling outcomes in terms of temperature reductions. It is fair to expect that most, if not all, of these scenarios will have some core benefits, and these core benefits are the additional benefits to the targeted lower temperature outcomes. For example, putting trees in the landscape improves the natural habitat in the area, which then enhances biodiversity outcomes. We know that trees are also good at reducing carbon pollution, and other studies have shown that reducing summer temperatures has some economic impacts through, reductions in energy costs, avoiding some productivity losses, and also just getting rid of impervious surfaces can lead to improvements in stormwater management costs. And we also know that, creating comfortable vegetated and grassed open spaces can stimulate people's engagement with physical activities through recreation or exercise. And over the long time, this could lead to material health outcomes and thus avoided healthcare costs to the economy. However, while we've got all these benefits, it is not always possible to put dollar values against each of the ones that you have identified. This is because sometimes there's just not enough data to estimate the benefit in a reasonable way. At times, there are no values that can be transferred from previous studies or other locations to your study area. And it could be that there's just too much uncertainty around the benefit, such that an attempt to assign a dollar value to that benefit could deduct value rather than add value to your whole assessment process. In this case, the benefits that we have assigned dollar values to, there's 4 of them, and these are human comfort associated with cooler summer temperatures, carbon dioxide pollution mitigation through carbon sequestration, which is a function of the trees that are proposed to be put on the ground. And we also have 2 livability benefits, which are improvements in neighborhood amenity and enhanced recreation opportunities. Okay, I'll dive a little bit deeper onto those benefits that I've said we have quantified. The first one, which is the valuing the human comfort benefit. This was based on a research done in Melbourne and Sydney to estimate community willingness to pay for cooler summer day. We adapted the findings from this study, which was done by Brent and others, and it was published in 2016. So we adapted that to the Proserpine region. We then used the modeled reductions in UTCI from Steph for each of the scenarios, and we adjusted the values from this Sydney study to the Proserpine area, taking into account inflation since 2016 when this study was done. and also looking at the differences in household incomes, because that will affect people's willingness to pay. It is also worth noting that this Brent study that we relied on for this benefit is part of the research outputs from the CRC water sensitive cities, where the heat modeling was also done. Okay. Then we have the CO2 pollution reduction. This benefit was based on estimated value of carbon abatement from a report by the ACT Climate Change Action Council. We adopted a social cost of carbon, which was around $70 per ton. We then used indicative and conservative estimates to reflect the amount of CO2 that each tree could capture, and that information was based on another report from Canberra, from the Department of Environment, Climate Change and Energy. The livability benefits, there's two of them. The first was the enhanced amenity. We know that vegetation contributes to improved neighborhood amenity, which can have a positive impact on nearby property values. So for the three scenarios, we captured this benefit using a percentage impact on nearby properties. And for this case study, we had 33 properties that we judged as potential beneficiaries. This low number of properties reflects the fact that our case study area is dominated by the town center, which has quite a bit of non-residential developments. And we used a 3% value for measuring this benefit based on published studies. The second livability improvement benefit was to do with recreation. The irrigation scenario, changing of hard surfaces to grass and changing hard surfaces to grass and trees, are expected to provide additional space and opportunity for locals to recreate. This is an important benefit that is, however, very difficult to measure for our case study area. Compared to the other benefits, it had relatively large amounts of uncertainties. For example, how many people would use the space? Where will such people be coming from? How often would they use it? And without these proposed scenarios, will these people still engage in recreation at another outdoor public space site? Because all that affects how you then go and say, okay, by having these scenarios on the ground, this is the additional benefit. So rather than making up all these assumptions, we instead worked out how much recreation value is required to get a benefit cost ratio of 1 for the relevant scenarios. Next one, Steph. So in this slide, we can see that green walls are the most expensive option, followed by white pavement and car parks. These costs were estimated over a 30-year period, which is a standard appraisal period if you are doing a benefit cost analysis following the Queensland Treasury guidelines. And we discounted our dollar values using using 7%, a 7% discount to just bring them to today's dollar value terms. And the value of cooler temperature was estimated for all scenarios, except where there was an overall increase in temperature, like the white roads, or the cooling outcome was generally very small compared to the cost, e.g. your green walls and mistings has 0 degrees Celsius in terms of UTCI changes. Street trees and irrigation have a net present value of greater than 0. This indicates that the costs and benefits that we accounted for in the model, the costs are lower than the benefits accounted for in this model. So overall, these two scenarios are performing better than others. The irrigation benefit we captured is the cooler temperatures, the amenity improvements, and carbon pollution mitigation outcomes. Next one, please. Okay, now in this slide, we are presenting the benefit cost ratio, which is a comparison of, okay, how much are you putting in as an investment and how much are you getting out as a benefit? And we are also presenting a range for this benefit cost ratio value the range is useful for testing whether the viability of any of these scenarios is influenced by the uncertainty that we have built into our modeling. Like I said earlier, there is lots of assumptions that we have to go through to come up with some of these numbers. So what we would typically do, we would say, okay, this is your most likely value for your input parameter. Worst case scenario, or your low value is this much, and the highest you could possibly achieve is this much. And then we run the model through what's known as a Monte Carlo simulation to just work out if maybe, for example, for those that are not viable, if you mix and match the different combinations, does that actually change the outcome? Does that turn that scenario from not viable to viable? Okay. In this case, our sensitivity analysis indicates that it does not really change the outcomes. The results indicate that street trees and irrigation of grass areas are the best scenarios in terms of economic outcomes. At the bottom of the table, we see that recreation from new grassed areas and irrigated grass and tree areas are also potentially viable. But these last two benefit cost ratio results are dependent on whether there's enough additional visitations or people who will recreate at the site to offset the costs. That's it on the benefit or the economic side of things. Steph, I will let you then jump on to the next slide on recommendations.
Thanks, Biani. So this is our final slide. I thought I'd run you through some of the recommendations that came out of our analysis. So generally, trees were pretty much the winner, I suppose. They created, they were really good cooling results. They were a very cost-effective solution. So when considering planting additional trees in Proserpine, it's worth considering east-west oriented streets as a higher priority than north-south streets, purely because they receive overhead sun throughout the day. But also, as we know, trees take a little while to get to maturity, so it's worth considering other cooling options while the trees are growing. In terms of irrigation, it was definitely the most cost-effective solution and it produced some good cooling results. We would recommend that perhaps irrigation for cooling is triggered when the air temperature is expected to exceed 35 degrees. You could, do irrigation the night before to try and help cool down the day. Next, water fountains and misters. We didn't talk through those results in this project, but basically they were really effective as a localized cooling, but once you moved more than a couple meters away from the source of the water, so like the fountain or the mister, the cooling effect kind of dissipated quite quickly. But when you were close to them, cooling was about 1 degree. So it's worth considering something like water fountains and misters, perhaps for localized kind of spot cooling. Maybe you have a busy thoroughfare, and if you place them to the north of the hotspots, they'll be able to create a nice cooling effect where they're needed the most. In terms of the built environment, it was a bit of a mixed bag. So as we saw, painting surfaces white does reduce the temperature, but it can increase glare issues. So it's likely that the best results will come when you're combining a white surface with something like a tree. So you're having this lighter surface, it's not absorbing as much solar radiation, but you're also having some trees to offer some shading from the glare. Also, changing a hard surface to a natural irrigated grass or trees is quite a cost-effective solution as well. And I think just generally, we've spoken a lot about the town area, but the forested areas to the north of Proserpine are up to 3 degrees cooler than urban environments. So it's also worth just considering maintaining and expanding these natural areas, as they're also equally important for cooling. So that's it from us.
Thank you, Steph and Bayani. That was a really interesting presentation, and I hope that everyone has gained some useful insights from that presentation and extended their understanding of how heat can be managed into the future. I personally found it very interesting, considering that potentially we may be using irrigation as a tool for managing heat into the future, and we at council are now going to be looking at all of these results and looking at how we can use this information across our region and through our projects to try and manage heat throughout our communities. So I just wanted to throw the floor open now. If anybody wants to ask any questions, you can jump in now. We've got a question on the chat. Tim, did you want to ask the first question, and I'll read the chat?
Yeah, sure. Thanks for the presentation, guys. I'm from Mackay Regional Council. Just had a question around, I know you looked at green walls. Did that also include like green roofs as well? I know this part of the world we haven't got a very good uptake with green roofs to date. So I just wondered on how that was considered or potentially to look at in the future as well.
Yeah, so we only looked at green walls. We didn't do green roofs in this situation. That was something that came from council, I think. But yeah, they were an interesting thing, and the results didn't show a great cooling effect. If there was a slight cooling effect, it didn't really travel very far from the wall, and that is consistent with some of the literature out there. So in terms of, there's definitely benefits, but whether the cooling benefit's probably not their number one benefit.
Mm-hmm.
I think it's worth noting as well that this study was obviously done on the town scale. So the effect of cooling the town, of painting your roof white, wasn't a cost viable solution for us to to look at trying to encourage residents to all paint their roofs white for the cooling of the town. However, it may potentially be something that's viable for the individual householder, because there's been a lot of evidence to show that you can get, sometimes I think the studies are saying 20 to 30% reduction in temperature within the individual home by painting your roof white. So I think those kind of that kind of work may need to be done on a household level to really quantify the benefits of things like green roofs and white roofs on the individual household. And I know Townsville Council's done a lot of work on white roofs. So yeah, we may be able to get some information at the household level from that.
Mm-hmm.
I've got a question in the chat from Vivian Luxton. She's asking for some examples of irrigation. What would it look like and how would it operate? So I know Steph mentioned what she's modelled. Did you want to add anything to that, Steph, or did you want me to? I can explain what we're looking at.
Yeah, that'd be good. The model was quite a simple kind of, you just splash water on the grass in the model. But yeah, Olivia, if you could go into detail, that'd be great.
Yeah, sure. So Vivian, just to respond to you a little bit, we're looking at getting some smart sensors. So we'd be able to look at what the weather forecast is. So obviously we don't want to water in the morning if it's going to be raining in the afternoon anyway. But if it hasn't been raining and the soil moisture is low and we've got a hot day forecast with no rain, we would be looking at trying to trigger some irrigation that morning. So maybe from 2 a.m. to 5 a.m. We'd be triggering in certain areas that we've got the most vulnerable, that are the most vulnerable to heat, and we have high traffic. So areas around the walkways around the hospital, the walkways to school. All of our study was looking at heat at 3 p.m. So if we're trying to get those results at 3 o'clock when the kids are leaving school, then we'll be irrigating in the morning. So it'll be more of trying to irrigate those areas to get that evaporative effect in that afternoon happening. So we're looking at trying to work out how we may kind of get that infrastructure ready now to use it more as a irrigation as a tool. I hope that answered your question. Did anyone else have any questions?
I just have one, if we've got time. I suppose there was a lot of discussion around heat studies and what we can do now for current houses, but I suppose long term, having developers start to build, is there an avenue for getting some of this built into those design standards? Or I suppose next steps, looking at not just patching up what we've got currently, but future planning wise.
So there was some recommendations that we've pulled out of this study, which we're going to be putting forward to council as far as things that they can look at incorporating into the planning scheme. And there'll also be been discussions around, could there be some kind of climate ready standards for future development? So it may not be something that's mandatory at start. It may be a voluntary program. It could be a Climate Hub approved development program, who knows? But we have been discussing that about how we get that advice out and how we can almost reward developers for doing that, taking those actions, and to ensure that we are creating those cooler communities moving forward. So yeah, we're definitely looking at different ways to do that. Is there any other questions? All right. Well, I also wanted to acknowledge, while we're on the line, Don Blackman from Mosaic Insights, Mitch Perry and Jim Binney from NCE Economics, because they also all contributed to this study. So thank you to everybody. It's been really great working with everybody. And the information that's coming out is already being used. And I am also working on other programs and looking at how we can further extend this and use this information. We would love everybody's feedback on the study and how you may be considering using this information around your household or your business or your council area. So please share by email any information and keep communicating with us. If you're interested in any more information about the Climate Hub, please head to the Climate Hub website. We also have a Facebook page which you can follow. And as I said before, we are going to share this recording very soon on the Hub website as well. So if anyone wants to share this recording further with any of their networks, you can do so after. We'll probably have it up tomorrow. So thank you everybody for joining us. If nobody's got any other comments, we may leave it there.